Thank you so much. So welcome back. This is lecture number 3 of this lecture course. Yesterday we discussed the type chain. Continued discussion of the type chain. We discussed something that is not directly relevant to today. We discussed how topology appears in momentum space. We found this binding and the mapping from the Brillouin zone to the space spanned by the Hamiltonian. And then we continued with this more general definition of characteristic feature in SPT phases, which is can be explained with this methodology of symmetry fractionalization. So what we did is we started from the usual p-type chain. We saw that the relevant symmetry is just the parity, which is a Z2 symmetry. And then we found that the symmetry in the infrared, so when we look just at essentially the ground state or the ground state manifold, the symmetry fractionalizes, and there's a contribution coming from the left edge and a contribution from the right edge. From there we went on to generally discuss this concept of, or introduce this concept of symmetry fractionalization. So your original model, your lattice model in the UV has a symmetry, some symmetry is called U, and they're just a direct product of U's acting on each qubit or permanent Hilbert space locally at each satisfies separately. And of course, there is a set of U's and they have a certain algebra. And then the point about symmetry fractionalization is the low energy sector, this symmetry fractionalizes into operators which act only at the edges. Moreover, these operators now, since there is a product here, they need to suffice the group algebra of the original U's only modulo 5 phase vectors. So that's called a projective representation. Let me remind you, I didn't write this out explicitly yesterday. A projective representation of a group has the property that usually when you have the representation of concatenation of group elements, usually this is just R of G times or dot or whatever R of H, right? That's a representation usually. If you have a projective representation, there can be phase vectors, which can depend on these elements G and H. G and H are some group elements, and the representation, projective representation has this extra thing. And these phase vectors appear. In particular, they appear in the example that we discussed of the p-type chain. And they will appear again today. Now, when we have bosonic systems, the ULs and the URs are completely decoupled, they commute with each other. We saw that in the example of the p-type chain, we had essentially the parity represented by a single Majorana on the left and another single Majorana on the right. So these two guys anti-commute. So for fermions, there is the potential that there are some symmetries which anti-commute. I put bosons here in quotation marks because I had a question afterwards. We would have an example for a bosonic SPT today, but bosonic here is used in a very loose sense. It means just that the operators acting on different sites commute with each other, but spins also count as bosons in this sense. So the word boson in this sense does not necessarily mean that there is a commutative EV dagger equals 1. Okay, then we went on with this, and we used that if additionally to parity symmetry we impose time reversal symmetry, we find that also time reversal symmetry can fractionalize, and then the possible representations of the algebra of parity symmetry and time reversal symmetry allow for 8 possible phases, SPT phases, including the trivial one. So that leads to a Z8 classification, which is sort of the algebraic reason for the breakdown of the 10-fold way from Z to Z8 in this particular symmetry class upon inclusion of interactions. So, we originally had planned to discuss with you a little more details about the Getaev model and the mapping between the Ising chain and the Getaev model in particular in regards to boundary conditions, and make a connection to non-invertible symmetries, which are symmetries which, well, as the name suggests, cannot be inverted. So clearly that's something that is beyond Wigner's theorem. we won't have, I think it does not make sense to spend too much time on this, so I decided to move on. It will be included in the lecture notes. The Kitaev chain was an example for, well, it's essentially a topological superconductor. We saw that it looks like a superconductor, right? It has edge states, fermionic edge states. It's essentially a free fermion topological superconductor, and in this sense also a fermionic SPT. To complement this, I thought it would be useful to spend today's lecture on a bosonic SPT, the paradigmatic example for a bosonic SPT, and conclude with, we get there, some topological proofs, so use topology for some proof and some related spin chains. Okay, so having said that, we move to chapter 3. So we look at spin rotation variance, spin rotational variance, spin chains, and what we'll have here is bosonic SPT, and we will also discuss a topological proof. Okay. So first part is antiparamagnetic spin-1 chains. And we will use the AKLT construction for that. Actually, we will discuss spin-1 half chains. And at the very end of the lecture course, I will use field theoretic arguments to essentially explain the difference between spin-1 half and spin-1 chains, following what's known as Haldane's conjecture. But to make direct connection to what we did last time, let's start with symmetry fractionalization. And the possible phases that we can have. Possible gap ground states. Okay, so in fact, I'm doing something slightly more general than what I wanted to constrain myself based on this title. In principle, we want to speak about spin-1 change, so we have an SO3 symmetry. But for the discussion of the symmetry fractionalization, so for the sub-chapter 3.1.1, it's sufficient to look at a Z2 cross Z2 subgroup of SO3. So let's consider Z2 cross Z2 subgroup of SO3. And this subgroup is just 1 Rx, Ry, and Rx, Ry. So these guys here, that's what I think, use some colors to sort of distinguish this one here. Okay, so these here are, and this is version also, pi rotations or y, right? So that means that our x can be represented as 1 minus 1 minus 1, and our y is minus 1 minus 1.
This is what is called Clifford algebra.
No, Clifford algebra means gamma I, gamma j, anti-commutative group. Now it's a question of normalization delta I.
Yeah.
Anti-commutative. In fact, here it's important that our x and our y do commute. So we have the property of this algebra is our x, maybe write this one. Our x, our y equals our y, our x, and our x squared equals 1 equals our y squared. Okay, I should maybe say that, so what we'll speak about is this, so the topological phase that we speak about is sometimes called, as I said, the AKLT phase, for, I will explain the acronym later, that's the exact solution that we will discuss in a second. Sometimes also called the Haldane phase of spin 1 phase chains. And for this symmetry-protected topological phase, there are various ways of discussing symmetry fractionalization. This is one of them. And I'll try to actually concentrate on the most important bit of it, which is essentially this part, which has a non-trivial projective representation in the topological case. So what we do is, we do something similar to what we did yesterday. This here?
Yeah.
This is a weakly line, so it means anti-commutator.
So here should be minus.
No. He asked me about Clifford algebra. This is the Clifford algebra. And I'm saying that our x and our y commute. Just look at these matrices that are diagonal. Yeah. So this here is a side remark which has nothing to do with the lecture, it's just an answer to this question.
Told you that they were worse.
You just told me where this is?
Yes.
Thank you. Okay, it also reminds me that I should repeat all questions so that everybody knows why I'm writing things on the blackboard. Okay. Here. Just a second. Things are inverted here. Okay. So, right. 13. Okay. Let's assume fractionalization. Symmetry fractionalization. So ansatz, we write our mu equals our mu left, our mu right, the mu equals x and y. These guys are bosonic, so we can actually just look at one of those separately from the other. Doesn't really matter. Okay. Then,
Excuse me for a moment.
yes.
Which symmetry fractionalizes?
So these are our group elements. I'm fractionalizing all of those. This index mu. So the symmetry that fractionalizes is rotation. The symmetry that is of relevance that we discussed is the Z2, Z chorus, Z2 subgroup.
I agree that this is our symmetry.
Sorry. This is our subgroup of SO3, so that's the symmetry. So the full isotropic spin chain has SO3 symmetry. Sufficient to discuss. So in principle, you can add perturbations to your model, which still preserve this, so you can make it a little bit easy, or easy access or easy plane. As long as you preserve those, the consequences still persist.
Could you somehow clarify what means this U fractionalization?
So what we do is essentially, okay. So we had a set of assumptions here, which was essentially that we have a gapped unique ground state in a closed boundary condition. In open boundary conditions, in principle, there can be edge states. So then the symmetry acts effectively only on the edge states. So then the low energy sector it fractionalizes. So the assumption, this word assume, encodes the assumption that we have a gap from the ground state. And potentially there are edge states, there can be also no edge states. the assumption of the, I mean, we will see that there something that comes out is also a possibility of having no edge states. Or that symmetry does not impose the presence of edge states.
But it could be F state without any.
That's right. Then the symmetries will be just trivial. They will just act trivially. The representation will be just because there is nothing that they can act on, no Hilbert space that they can act on, so the representation is just a trivial representation. All group elements are going to be represented by the number 1.
We always say that it's not to just fractionalize the numerators of the group. That's one thing. I guess the general statement.
This was a question or a comment?
Question.
So, but then the answer is yes, right? Yeah.
But actually, you wrote, so do we exclude Rx times alpha equals?
No, it's in principle also true for these guys. We will actually now see that, so the main question that we will discuss is how is this guy going to be represented? I mean, it's going to be still, this here is the product of these two guys. But as I just said, these products, if you have a projected representation, I can get non-trivial phase vectors, and maybe non-trivially represented, and that's exactly what we'll see now. So for the moment, I just fractionalize these two, and we will try to find out what are the consequences of fractionalization of these two for the algebra corresponding to these two. So, because in principle there is this, right? There's also this. In the bulk, it doesn't matter if it's the same. In the end, we will see it's actually not the same.
And we can clear why it's enough to consider as a subgroup. Or is it a choice?
That's a choice. That's a choice. To make things simpler, essentially. And as I said, you could have chosen also something else. One can also argue, for example, that one can take time versus symmetry to find the edge states as a protecting symmetry for these edge states. So the question is essentially you start from a symmetric model, you start making it more and more non-symmetric. And which are the symmetries that could potentially still protect your edge states? So I could potentially maybe break time versus symmetry as long as I keep these guys. Or reversely, I could break these guys here and retain time versus symmetry. But I decided to present here this subgroup.
Is there any rationale behind choosing discrete subgroups? I mean,
Yes, there is a rationale behind it, namely that the symmetry fractionalization is sort of what is designed for discrete subgroups, but it works better for discrete subgroups. And on the other hand, I mentioned before that there is, so first of all, this business is sometimes also referred to anomalies. I prefer to use the word anomaly for quantum field theoretical anomalies. For quantum field theoretical anomalies, we somewhat more easy to think about. We have global continuous symmetry, such as U1, let's say. Then you gauge it, then you look for anomalies. So, what I'm trying to say is essentially that these discrete subgroups sort of more suitable to this methodology. Continuous subgroups a little bit more suitable to the looking for quantum field theoretical anomalies. But essentially, as I said, even the nomenclature is sort of now overlapping. It's essentially two phases of the same thing. Yeah. So, but the short answer is I'm taking discrete subgroups because I have just a finite number of elements which are sort of.
so it's easy to just classify all the possible representations.
It's easier, yeah. More like for. I'm trying to do the simplest possible here. Right?
I mean, for this particular model, we just choose this particular group because we know it classifies everything. I mean,
that's right.
Because there's, I think, maybe there are more.
There are more that you look at, of course.
Yeah, but those are probably boring and just give nothing.
Yeah,
or just a clever choice.
Yeah, which is, I mean, it's a choice that is not even my own, which I found as the easiest one in the various pedagogical summaries. Yes.
What does it classifies everything?
It classifies everything. Classifies all possible phases. Yeah. So the question is whether, in principle, if you had a bigger subgroup, whether you could get more phases. I think that's this question. And I think this is all we get all that there is essentially. But most importantly, we get the non-trivial Haldane phase, which is the one that we're after. Okay. So, yes.
How abstract is this procedure? Like, how much are we going to rely on the physical and the fact that we have left and right, or could we just say, hey, here's groups, they do by two, and we can do this abstract mathematical procedure?
So, what is physical? At which level of physicality you ask? I mean, physical boundaries are important, of course, and we will get some physical consequences, which are edge states. We will actually discuss how these edge states will transform. We will actually see a transmutation of spin, spin statistic of spin.
Okay, but is this an interpretation, or is this a part of the fractionalization? Like, can we do the fractionalization and just make it an abstract mathematical?
So far, if you want, I mean, we have this abstract mathematical methodology, and then we will extract some physics out of this in the same connection, I would claim. So this here is a chain. Maybe I tell you the answer already ahead of time. Maybe this answers your question. We are speaking about a spin one chain, right? So we will have a bunch of spin ones next to each other and interacting with each other. And these arguments can show you that the edge states are actually spin one halves. And spin one half is, so this is a fractional, this is part only of spin one. So somehow, out of objects which are spin one, you get a spin one half. So that's a physical consequence, I would say. Okay. So then what we know is that R mu is, I concentrate on the left edge, doesn't matter which one. R mu L squared, it has to be proportional to 1. There's also going to be a phase. This phase is not important for what I'm going to discuss with you. But in principle, there's also a phase. But it has to be proportional to 1 to represent this. Now, what are the possible representations for this guy? Okay. So, in order to see that actually, so what we say is that the other thing that there is this Rx, Ry, in principle, can be some phase times Ry, Rx. And we will now use that this is proportional to unity to fix the possible values for this phase.
Could you please clarify? You start from isotropic spin chain, right?
Not necessarily. I mean, here I allow potentially symmetry breaking terms which make it easy or easy access. I can reduce the symmetry, and the consequences still persist. So essentially what I'm saying is we will find edge states which are protected by this symmetry. So you may break down the SO3 to something smaller, perturbations of this type will not lift the edge determinacy.
But what you're basically saying is that Rx, Ry, and Rx, Ry are the symmetries of the whole system.
So for the discussion of this 3.1.1, that's the symmetries of the whole system that we want to consider. But somehow I wanted to discuss the more general case of spin rotation invariant spin chains as opposed to the easy case that I discussed in the context of type chain. Maybe this title of chapter 3 is confusing you. For the moment, forget about it. Just look at this.
Excuse me,
Yes.
how did you write the last equation?
What I did here?
Yeah.
So all that I did is I assumed there is a projective representation. Oh, sorry. There are L's here. Does that solve your problem?
Yeah, it makes sense.
And yeah, okay. And in principle, these are also alpha L's. Alpha rights might be minus alpha L's. So next, well, why don't I just continue here? So let's take the square of these guys here. So what we want to do is we want to see Rx squared L, Ry squared L. So this guy here, as I said, is proportional to unity. So we can bring our XL, one of these RXLs to the right. So it's going to be our XL, our YL, our YL, our XL.
Yeah, sorry.
Yes.
You assume some properties, yes, on the bottom right one. So I'm interested in how which properties should we expect to use this? I mean, that I can assume that XL is some arbitrary number and RYL is inverse of this number. I mean, he assumes that it's proportional to the sum.
When you say number, I don't understand. You mean this?
I mean, it could be not space. I mean, it could be some any complex number. But for some reason, you assume that it has more.
Well, I mean, if I'm saying it's projective representation, I'm already restricting myself to phases. Huh?
So this is, I mean, so for externalization, assume all of these and projection representation. Could you explain what projection representation is? Yes, I don't know what it is.
Projective representation is what is written in Greek. So usually a representation of a group, you know, it's a mapping from a group to some vector space, some operator spaces, acting in matrices, acting on vector space. And the property usually is that the representation of the product of group elements is usually it's just the product of the representation. Yeah. So that's what we usually have when we have like we have, for example, an abstract rotation symmetry, and we represent it either with, you know, say with SO3 or if you want also with SO2. So we have certain matrices which represent this, 2 by 2 or 3 by 3 matrices, and the concatenation of the group elements is represented by a concatenation, by a matrix multiplication. That's usually the case. And here, in addition, we allow for an extra phase. Why do we allow for an extra phase? Because essentially, because we have fractionalized, and essentially the phase left and right, they can cancel out. So sort of it has split into two parts. But then you can ask the questions, which are the projective representations? So it's, you know, there is representation theory, group theory. For example, for rotations, we represent all possible representations of the rotation group. And then we find that there are spin 1 half particles, spin 1 particles, spin 5 half particles, whatever. We do it also in high energy physics. We look at whatever representation of Lorentz, Poincare group or something and find possible particles. Okay, that's the standard way of looking at things. And then there are extensions of this procedure. You might know, for example, that we do this extension in CFT. We look at some extensions because we have, you know, central charge and so on. Here, we look at an extension which are just projective representations.
A very naive question. In usual quantum mechanics, we actually don't care about the overall phase of the wave function. Can we think that the quantum mechanics is actually projective representation?
Well, I think that people do discuss indeed that there are, yes, I think the answer is yes, that the representations in quantum mechanics are related to projective representations. But the question is, what are the implications?
Maybe it just turns out that in most cases, projective representations turn out to be like faithful ones without any phase, but in principle, nothing forbids me from considering more general cases.
I think what you're saying is correct. The only thing is that I forgot what the actual consequences are. So I think also what the last statement is also correct. I mean, usually we don't need to think about projective representation. They currently don't have a consequence. Here they might have a consequence.
Because maybe that's what's written in the beginning of the Weinberg book about quantum theory. That's what I think.
Possible. Good. So what I did here is step 1. So these were our sort of. We just have these 3 parameters, and actually only this one is the one that we will use for the classification. This one will not be important. So all that is important is that this one is anyways proportional to unity. So I could bring one of these Rx across, and now I want to swap these 2. Oh, now I actually use something different than what I was having before. Okay, yeah, this is the way. So when I swap it, I get e to the minus I alpha r xl r yl, right? But then I have here again r yl r xl. So that's another. So maybe I should do the whole thing here. So all of this here, let's do it in color coded. Everything is under the red bracket. Now I have r yl, r xl. I do the same thing again. E to the minus I alpha. Then there's another e to the minus I alpha. R yl, sorry, r xl, r yl, r yl. I've just done it twice. There was yx here, and then there's yx after that. So in total I get e to the minus I 2 alpha. Then I get again my rxl squared ryl squared. So you see, in principle, I said, okay, some projective representation. But then the consequences of this projective representation is that the only way that this is consistent is that 1 equals e to the minus I to alpha, or alpha is 0 or pi. These are the only ways that we can do it. However, the usual representation would be alpha equals 0. We see that alpha equals pi is also consistent. So then we find that there are two different representations. So we find, so the important bit of the story is that we have our xl, our yl equals plus or minus our yl, our xl, and then maybe a color code things. So let's do the plus in orange. Plus, that's the usual representation. As usual, it's non-topological. And it's consistent with no edge states. There is no necessity of edge states. With no edge states. Oh, I then write all the way from the left, right? Edge states.
Statement, it's consistent with no edge states, implies that I can realize this representation on Hilbert space of size 1.
Yes, exactly. And then the representation is trivial.
And the non-trivial one means that I cannot do this. I need necessarily at least 2 states.
Exactly. Because you cannot find just number which is going to be accumulating to itself. So, I mean, regular numbers. So the minus case is the situation where the anti-commute. And as I just said, by consequence, there must be two-dimensional Hilbert space. And in fact, it's easy to see that in this case, the good representation would be Rx equals I put an extra I, and it's obvious why in a second. Ry equals I sigma y. So these guys are anti-commute. We need this two-dimensional Hilbert space. So we have here neat two-dimensional Hilbert space, 2D Hilbert space, So therefore we have twofold degenerate edge states. How do I hyphenize degenerate? Degenerate states at the edge. And as you can see, this here is nothing but the spin 1/2 representation of my pi rotations. So we have spin 1/2. Yes.
For the carbon element only.
Yes, that's all it is. And of course, the same thing is true on the right. That wasn't your question, right?
Yes, yes.
Okay, yeah.
So, if you assume this to be valid for right, and the same should be for left.
Yeah, right and left has the same. So each of them have a twofold degenerate edge. So the overall ground degeneracy is fourfold. Fourfold. Well, 2 here and 2 here, 2 times 2 is 4. Okay. Yeah.
I think that sense is crucially different from previous example of Ivy.
So again, so the Ising chain that I introduced, the Ising chain is not an example of symmetry-protected topological phase. The Ising chain is dual to a fermionic topological phase, which is the Gittian phase. The Ising chain has no edge states by itself, in its own basis. It has only, if you go to the fermionic basis, because it's a non-local transformation, in terms of fermions, it looks like edge states. Then there is another crucial difference. When you have a fermionic, like a topological insulator or a topological superconductor, as in this case, you have fermionic edge states, and in particular this operations here, which are particularly good in 1D, you see that the structuralization is of this fermionic type, such as these operators at the edges, this symmetry is anti-commutative. That's also a crucial difference to this one. So on the right, we will also have some sigma x and sigma y, but in a different Hilbert space. So we should maybe call them tau x and tau y or something like this. Right.
So may I ask a very simple question? We do not assume that fxl is the symmetry of the whole system. The symmetry of the whole system is fxl times fxl. Correct?
I didn't understand. XL, you mean RX?
Yeah, fxl is not the symmetry of the whole system.
Yeah, so this is sort of
Just the whole system is just an behavior.
just a second. I think the answer is yes, but let me emphasize again what we have done here, right? So we have originally symmetries of the whole system. That's like this guy Rx, Ry, without subscripts. They act on the whole system. And then we then know, well, there is a spectrum, there is a gap, and we can go below this gap. We want to look at states which are below this gap and how the symmetries are going to act on this subset of states. And then we look at these Rx and L and Ryl, etc. We assume sort of, it's an ansatz to say, everything must be living on the edge because on closed boundary conditions there is nothing. There's a single ground state. So if at all there is some degeneracy, it must be at the edge in open boundary conditions. So it must be such a fractionalization ansatz. And then you have projected it down to this thing. If you want, RxL is something like projector on ground state manifold, Rx, projector on ground state. Now I don't know if this is in your language something that acts on the whole system or not, but it will ultimately be.
You assume that if I would act of my fxl on my ground state, I would again get a ground state.
You get another, it's a ground state manifold, so you get another state in the ground state manifold, potentially. Yeah.
So it means like the group Z2 times Z2 turned into 2 copies of itself.
Yes, but moreover, it also has, yes, and a weird representation. Because it has this projective representation.
So where here we assume that we are looking to the states those gap.
In the ansatz, essentially. So all of this structuralization is, and I write low energy sector. So when I write low energy sector, I mean that there is some energy that I can say the word low with respect to.
Okay.
Right? And this energy is the gap above the minimum ground state, or ground state.
And why in the low energy sector we have the symmetry that is product of the symmetry of the left and right?
So we know that this is another assumption that the system on closed boundaries, without boundary, closed periodic boundary conditions, closed manifold. In that case, it is single ground state. This is another assumption for SPTs. So therefore, when I open the system, all the low-lying excitations, if there are any, they cannot be in the bulk. So they must be at the edge. So then it makes sense to say, okay, so there must be such a fractionalization. That's sort of the rationale behind course, a priori there is no guarantee that there will be edge states, and in fact, trivial representation is something that can come out as an orange chip. But we also saw now that this very general assumption can lead to the presence of protected edge states. And maybe let me emphasize again, this is, as always when you do something based on symmetry arguments, there's no big assumption on, the Hamiltonian. This is really a very fundamental statement independent on details of the Hamiltonian. So even if you don't know how to solve the Hamiltonian, if you know its symmetries, you can infer there are edge states or not.
What would be the physical elemental excitation signal, which is according to chain, we have to combine the two different modifier levels in a special way to get an effective
Yeah.
Now we have spin 1/2.
That's right. So we start from a chain which is spin. Let me draw this here. We'll use it in a second. We start from a chain. I will use side xi. 1, 2, 3, 4, L. Again, this L is the last side, and that L means left. And on each of these sides, we had a spin 1/2 originally. Spin 1. Right? So there are spin 1s, they might want to interact antichromatically, something like this. And what we find is ground state we have here a spin 1/2, and I should represent it as a small spin. And here we have a spin 1/2. And here we have a gap. So here we have a gap. So what it means for the overall, if you just diagonalize this thing here, the spectrum that you get is going to look like this. You have 1, 2, 3, 4 states, then you have a gap, and here you have whatever other states. This is some other states up here. There they are. There is a gap here. But we have 4 states down here. These 4 states are the 4 possibilities of, up, down, up. Yes.
How do we make that illusion for the bottom part, like if this operator is compute? Why there's no H state?
Not necessarily. So this is consistent with having no edge states. So you can have the situation where there's just nothing. In principle, spin 1 chains can also be in a trivially gathered situation. So without edge state. This only tells you that it's symmetry consistent to have edge states. And if you have no edge states, then you have, as I just said, that the one-dimensional Hilbert space is represented by just the number. Every group element is represented with number 1. And there is nothing. So, which is consistent with orange. So, I should also say, generally, this classification business, whether it's in this format or for the tenfold way, Pasha will probably discuss with you how you get it from the sigma models. You get a classification system which tells you that in a given, under the assumption of certain symmetries, you can have this many topological phases. It doesn't necessarily tell you that you are in that phase. That's a separate question, I think.
But do we have to choose symmetry or just the combination of
sorry, I didn't understand.
we have to choose this?
Yes.
We can create states in different ways.
Oh yeah, okay. So these spins here, this degeneracy here, is actually not a perfect degeneracy because across this gap, this spin can speak to this spin. So imagine this spin flips, and then flip, does some excitation here, and ultimately unflips this guy. So there is an interaction between this and this one, but it's exponentially small in system size because you have to go to L order derivation.
But we don't have the corresponding.
Just a second, I'm not done yet. What I want to say is, this is your splitting. So what you get then actually is if the interaction is effective interaction is antiparamagnetic, you have the singlet below the triplet. But the splitting is, so then this looks like this. This, and the splitting here is e to the minus gap times L. Is that your question? Sorry. And now it's and obviously the black and the SC equals 0 triplet, they are linear combinations.
It helps. And then another question is whether we also have to take care of the combinations that we make are physical, which is so for the Majorana fermions we couldn't choose any kind of combinations. We need to make sure that these are actually fermions, so we can only see how good it is.
I see. I think the question was, you were, first of all, I'll repeat it for everybody, and secondly, tell me whether I understood it correctly. For the Majoranas, what we do is, because each Majorana only has Hilbert space of sort of square root 2, we combine left and right Majorana to make a non-local fermion, and then the Hilbert space essentially is this non-local fermion occupied. And the question, I think, is it necessary to do this here too? And the answer is essentially not necessary. Because essentially, I think the fundamental reason is because we have these bosonic representations and the left and the right edge, everything commutes, so you don't necessarily have to do this. Okay, let's move on. And what I would like to do next is to show you a model which has exactly this feature. An exact solution for this model. The question is, where do I write this? Maybe I write it here. So I hope you realize that this is something crazy, that we start from a spin 1 model, and suddenly we find that at the edges, and you can have spin 1 halves based just on symmetry. This is allowed. So I think this is pretty amazing. You would think that when you start from spin 1, you can only have spin 1 or spin 0 or spin 2 or pi or something. Remember, you have spin addition, right? So spin addition means that you add spin 1 with spin 1. I mean, the direct product of 1 and 1 is 0 plus 1 plus 2. Right? So how do you get this 1 half? Pretty amazing. So, okay, so this is the AKLT solution of a certain spin 1 chain. So this is, let me write out once at least the names of these people. Affleck, Kennedy, L, Lieb, and the last person, the one that I know least, is Tasaki. This is late 80s. So maybe the history behind the story is that, I mean, I don't tell you things in a historically accurate fashion. This symmetry fractionalization business is something of the early 2010s, and this here is something of the late 1980s, and the consequence, sort of a response to Hal-Eight's work of the early 80s. Yes?
I have a strange question. So when we have a superconduction model, yes, we have Majorana fermions, for example.
Yes.
And here we receive from bosonic, again bosonic on the fermionic excitation. If we take
the word fermionic is in quotation marks.
Yeah.
I think you think of spin statistics, but keep in mind that spin statistics theorem assumes Lorentz symmetry.
there's no end here. But like down there. And, okay.
But on the other hand, I see where you're coming from, and indeed that's where I wanted to get you all through, that you realize it's a weird thing coming out here. Yeah. The word fractionalization of the symmetry makes sense, because usually you can add 2 spin 1 halves to make a spin 1, but now we somehow took a bunch of spin 1s and got some spin 1 halves out here. And in the case of the p-type chain, if you think of it as a superconductor, we had just have usual fermions, and suddenly we get half a fermion, which is a Majorana at the edges. So we can sort of pull them apart. Good. So up again, we need the Sasaki AKLT chain or solution. Say solution. Okay, so what Hal-Eight conjecture, and we will get there at the very end of the lecture course, is that spin 1 chains are gaps, spin 1 half chains are gapless. We will see actually proof for that hopefully today. And then for the spin 1 chain, actually, we will also see based on field theory, you can expect that there will be spin 1/2 edge states, at least in a certain case. And we saw that this is consistent, that we can have spin 1/2 edge states based on the symmetry fractionalization constraints. And now we just look at a Hamiltonian which has exactly this property, that it has, and we can solve it exactly. And it's a spin 1 chain. It has antiparomagnetic interactions, but it has actually also bilinear, so biquadratic interactions. So H equals J sum over all I 1/3 plus 1/2 Si dot Si plus 1 plus 1/6 Si dot Si plus 1 plus 1 squared. So this is an antiparomagnetic. Okay, so first of all, this is a number. We don't necessarily care about the number, but it's useful to have it. This term here is just the spin-spin interactions, and it's antiparomagnetic. There's positive, J is positive, so the S's want to stay antiparomagnetic with respect to each other. This guy is a biquadratic term. This is allowed because it's spin 1. For spin 1/2, since sigma squared, any sigma x squared, for example, is 1, there is no notion of such a term. But in higher dimensional spin representations, you can have s squared, sx squared, for example, sz squared in spin 1. Sz is 1, 0, minus 1. So sz squared is 1, 0, plus 1. This is not 1, right? So in principle, the higher dimensional representations allow such biquadratic terms, and then even higher can allow even like whatever it's called, triquadratic or something. Okay. This is chosen very, obviously it's not by chance. The reason why this is chosen is that this is actually projector. So this thing here, all of this here, is actually projector. That's the reason why this problem is soluble. Projector I plus 1, and this projector projects onto the spin equals 2 subspace of these adjacent spins. So let me write it out. This is, if you do the algebra, and I will not do it for you, but you're invited to check yourself, it's total I squared times is total I squared minus 2. And this total I is Si plus Si plus 1. So in case you've forgotten, when you have two spin 1s, and you want to do spin additions, you have these three representations that come out. So when you have, so therefore in this case, S total squared equals, so it's L times L plus 1, but L is 0, so it's 0. Here, S total squared equals L times L plus 1, so 1 times 2 is 2. And then we have here L times L plus 1, so 2 times 3 is 6. Am I doing it right? 6 squared. So sorry, this is 2 squared. Am I doing so? S and this is something I'm going to write here. What did I do wrong? S total. What did I do wrong here? I thought that this should be right. So 0.
Just
Somebody see what I did wrong?
without a square, just S times S plus 1 without a square.
S times S plus 1.
S squared equals S times S plus 1, where S is the number. So it's just
Okay, this is the correct answer.
Yeah.
Thank you. So it was a good reminder for myself. Okay, and then you see actually that this is 0 for when S total is 0 is 0. When S total is in the 1 sector, it's also 0 because of this bracket. And otherwise, okay, it happens to be this is 1, 4 times 6. Okay. Alright, so therefore, since this is a sum of projectors, the ground state, or the ground states, have the property that, so this guy is semi-definite, positive semi-definite, and they have the ground state. So if you find a state that has 0 energy, it's a ground state.
But you write that the projector depends on I and not plus 1, but on the right hand side it's only I and
This? No. This?
Ah, okay, no, I.
So I plus 1, so it's,
Yes.
yeah, it's implicit. Thank you. Alright. 14, 15. Good. So now let's construct the ground state for this model. So the construction works by taking this plane. I will get there in a second again, but so what I will do is I will write here. For the moment I will cover this, but then I will uncover it again and you can look at it. What we do is we essentially represent each spin 1 by 2 spin 1 halves and project onto the spin 1 subspace of this. So what we will do is we will represent, this is I, it goes from 1 to, that's very bad to call this L again, so that we call it lowercase left and right. So we have here on each side, we have the spin 1 halves. And we will call this here, so we have this everywhere. And then we have here I left and I right. So each side I, in this case I equals 4, is now split into 2 sides. And in each side we have a spin 1 half. And okay, so in total now we have 2 L lattice sides. And what we do now as the next step is we build a valence bond solid out of these guys. So okay, so first of all, let me emphasize again. So what we've done is originally we have a Hilbert space which has spin 1 everywhere. I'm now sort of solving a fictitious different problem where I have 2 spin 1 halves on each side. And I will later project back down to the spin 1 subspace of each of these guys. Okay. And what we take as an ansatz is a valence bond solid state for the spin 1 half. So what we have then is we will need the notion of this valence bond. We will call I right. I lowercase right. I plus 1 lowercase left. Singlet. This guy here is going to be nothing but 1 over square root 2 minus 1 over square root 2 sigma I left sigma, this is I right, sorry, I right sigma I plus 1 left and then sigma I right sigma I left. Note that for the cats here I use round brackets on purpose. So the round brackets are in this fictitious Hilbert space, which is this red Hilbert space. And when we get back to the actual, project back to the spin 1 Hilbert space, we will use the regular angular brackets. And what each of these guys is, so this is one of these bonds here, represents such a singlet between the right, so okay, to make this here I, okay, this is I minus 1 right. So the I minus 1 right and the I L have the singlet here, or here it's I right, I plus 1 left. And this is just a way of writing a singlet, but I use a matrix for that. So this is a matrix, and when I don't write anything, it means 0. Do you agree this is a singlet? I think it should be. Okay. So we repeat this over the entire chain, and get a valence bond solid. Valence bond solid. That is nothing but, maybe I use a name for this matrix. Let's call this matrix here. This matrix will be called R matrix. Let me just finish writing the indices for the R matrix, and then I take a question. I right, I plus 1 left. Yes, your question.
Second gets one.
That should be I plus 1. Thank you. Yes, thank you. Okay. So with the help of this matrix, we can write the VBS state. The VBS state at the moment is nothing but, forget about these. So these eggs, they represent that we are the original Hilbert space, the original sides are within a given egg. But we are essentially having a product state of singlets across the eggs. So it's easy to write it down. Right? And yes.
Could you repeat what VBS stands for?
Yeah, valence bond solid. Valence bond solid. So you know the word valence bond from benzene, I guess, right? Benzene has all the valence bonds, no? Not that I remember much about chemistry, but we call those guys valence bonds, right? And okay, but of course benzene itself has this valence bond. Benzene itself is simply this ground state, this position state, ground state. So that's what chemists write. We write as a position state, like a del state. But this is a single one. This is one product state. It's not a superposition state. Super, no entanglement. Good. The valence bond solid is the product of all of these guys. So product I goes from 1 to L minus 1 times R sigma I right, sigma I plus 1 left, sigma I right. So this is a big matrix, which is essentially the product of these guys here. I will write that, so it's big cat, which is the product of these cats. So I will use comma now instead of writing them all one after the other. So if I read up to 1 right, 2 left, 2 right, etc., 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 all the way to L left. And now I missed out 2 states. In the case of open boundary conditions, 2 states are left out. So that's here, it's sigma 1 left and sigma L right. Of course, if you want to do the same thing for closed boundary conditions, then just take one more R and connect these two fellows as well. Okay. Now, why is this a good ansatz for the ground state? So why is P, oops, this is P I plus 1 on a given singlet, or on VBS, equals 0. Well, let's take a subset. So let's concentrate, for example, let's concentrate on this guy. so of course everything is a product set of all of these BBSs. For the moment, let's forget that something is going out here. It might give us something. The only question is whether, assuming that there is a singlet here, what is the action of the projector onto this whole thing here? So this here, in principle, is what we have here. In principle, is a Hilbert space composed by 4 spins. So the Hilbert space goes from what? From 0 to 2. Other possibilities. However, this guy is already a singlet. We already know that these two form a singlet. So what you can get by sort of the composition rules of spins, when you have a singlet here, and you have potentially some spin 1/2s here, which are entangled over here, at most you can get spin 1. Because this is already a singlet. So then at most you get a spin 1. From this one with this one, we can get a 1/2 with a 1/2 fuses to 0 plus 1. So that means that blue box has only states of S equals either 0 or 1. Was the argument clear? So this one is already spin 0, so it does not contribute to the spin addition. So a 1/2 with a 1/2 is just 0 plus 1, so we can only have 0 plus 1. So whenever I act with this projector on any of these things here, independently on how this is entangled to this and to the side, we will always get 0. Excellent. So then the last task is to get back to the physical Hilbert space. And to get to the physical Hilbert space, I need probably more space. Yeah, I need more space. So we go back to the physical Hilbert space, and we use something that we call, maybe we should call it P twiddle, it's called P in the notes. P twiddle. So, okay, so this is going back to the physical Hilbert space, and we introduce this matrix M, which I'll define in a second. And it has indices sigma I left, sigma I right. It has spin equals 1. With projection Si, so this can be 0, 1, or -1. And then it does this. So we take sigma I left, sigma I right. And the matrices, so okay, so maybe I should explain. So first of all, I will probably omit this S equals 1 in the future. When you see an index S, that's a spin 1 index, so it can take values -1, 0, or 1. So it's element of -1, 0, or 1. And these matrices, I will give them in a second to you, are just the matrices how you combine two spin 1/2s to a spin 1. So that's by putting them both together, up or both down, or up, down, plus down, up. So let's just write this out explicitly. So M sigma I, well I write it. So these indices are now represented as a matrix. So for S equals Si equals 1, the matrix is 1, 0, 0, 0. So you only get a contribution from both being up. This is sigma, so this is the sigma I left, this is the sigma I right, and this is up, up. And I hope this is obvious. MSI equals 0 is something like this. 1 over square 2, 1 over square 2, and MSI equals -1 equals 0, 0, 0, 1. This is just a way of writing up, up, or down, down, or up, down, plus down, with the 1 over square. And what we have to do is we have to take this state and protect it. So the ground state can be obtained by projecting the VBS state like so. So it's going to be product over I equals 1 to L minus 1 M S I sigma I left sigma I right. Then we have R sigma I right sigma I plus 1 left. All of this product. Then there is one last M S L sigma L L sigma L R is 1 S L. I can also write it as follows. Just let me just write this one more question. Take one more line in case there's a question. We can write it as a big product of matrices. R 1 is everything. It's 1 L. And there are 3 indices here. Sigma, let me emphasize this. Sigma LL, LL, sigma LR.
Can you give a formula of like for that?
Can you repeat what you just said?
Can you repeat the formula? Yeah.
So what this is the projector. So okay, so what we did is we solved the problem in this fictitious red space, in which we have just by hand split all of these spin 1s into spin 1/2. And what we want to do is sort of we want to enforce Hund's rules and make them a big spin. Right? And this enforcing Hund's rules is this projector P fill. In the red Hilbert space, we found the ground state. It's just this valence 1 solid. But we have to project it back to just a spin 1 subspace on each of these X. This guy here projects into the spin 1 subspace. How do we see that? This is nothing, this thing here is nothing but writing if S equals 1, then this state here, this is the matrix. We have to contract with these lines here. It will be up on the same I, on the same side I. This matrix will be the one if Si equals 0. It's the matrix up down. I mean, it's a matrix that upward contraction gives you the bra up down plus da. And similarly, this one gives you the down. So then this here is the projection. So this here equals product over all P triple I on VBS. And then in the product I've taken, so this guy here, I've contracted these fellows, all these. Yeah, I've already contracted all of my round cats and bras. They have just a regular, orthonormalized basis.
Wait, what do you mean round?
So I have introduced for the red space, I have used the notation of round. This is a round bracket as opposed to an end bracket. This is just to distinguish the fictitious space from the real space. And we have contracted all of the indices. And thereby we now got back to just the original basis. The original basis is the basis in which on each side we have 3 states possible represented by S1, S2, and S2. I mean, S1 being minus 1, 0, and 1. I don't know who's first. Okay.
What state is this now actually? Because we think we're looking at the ground state by acting on any state.
No, we didn't act on any state. We acted on the one which was the ground state in the fictitious Hilbert space. So we used the fictitious Hilbert space as a means to construct the ground state. And then subsequently we projected it to get into the right ground state.
Where does the state S1 to S0 come from?
This state here, okay. This is not any state, right? So this is indeed, these are all the basis states. So the set of all of these guys here are all basis states. But we are contracting them in this very non-trivial fashion. This is not just something. So you see, there is this, maybe this is not here. There is a sum in the repeated indices are summed over. So S1 sums with S1 and blah blah, SL sums with SL. Yeah, sorry. Einstein convention is used. I should have said this. Here also, Einstein convention is used. Maybe that was also complicated before. We are contracting these indices. Yeah.
This matrix is R and M, they do not come in.
R and M, they live in different units. Well, I mean, the R, I see. This sigma here, no, they don't necessarily commute. They don't necessarily commute, no. In fact, R is this, well, but they don't really live in the same Hilbert space. They have only one index in common, right? So maybe I should now, well, let me take the question and then I give you a graphical representation of what happened.
And it's just tensor, there's no need to speak about commuting.
Yeah, they are not, yeah, exactly. So I'm going to draw the tensor network representation of this matrix question.
Yeah, question. Why are we in this trick, which is like a general thing that people speak on systems? Is there
okay, so there are 2 reasons why this. First of all, this is a trick which was used to solve the problem. And the second reason is what I want to get to now. This is the simplest example of a matrix product state. And matrix product states, I mean, I don't use them at all, but they're very big in the community, they're used a lot. This is the way to write MIT, etc. So I thought it's useful for everybody to see that. Yeah.
So if you consider the China, yeah, so there is 116 term.
Yeah.
But in principle, you can write any number there.
Then it's not, yeah.
Let's say kappa. And kappa is a continuous measure in one model, which is not solvable, but there is no any phase condition that goes to the matrix from this phase to the I mean, if you start to write parameters, there is no phase condition from the T model to the Heisenberg model. So that's why Heisenberg model has the same representation as the T model.
Okay, thanks for highlighting. So in principle, we would like to solve. In principle, in the 80s, there was this Haldane conjecture that spin-1 chains. First of all, they are fully capped, and second, they might have spin-1 half-edge states. So how do we find out? And it turned out that there is an exact solution, but that exact solution is not the Heisenberg chain itself, but it's something which is in the same phase, where phase means no phase solution. Okay.
Is there an intuition here and why this is the ground state?
Well, the intuition, I think, well, I mean, intuition in the red representation, I hope it was clear that what we wanted to do is we want to get on each of these bonds no contribution of the S equals 2 center. That's it. I don't think there is more intuition behind it. These exactly soluble models, they're somewhat contrived. At the same time, they give you, you have something in hand, you can do the calculation and you can see that something comes out. So I promised a picture there.
So you just distribute the sigma 1 and sigma all left?
L, so yes, that's right. Thank you. 1 L, L R. Okay, so let's represent this as a graph. So what's usually done is this. So we have, so I draw it here, but it's this thing to represent this. And maybe I should use colors. So we have these matrices M, They're not matrices, they're tensors actually. They're matrices at a fixed SI. So they will be represented by boxes. And these boxes have three indices. There is SI, and then there's sigma I right and sigma I left. These are the red ones. They are given here, given here. Well, that's maybe pedagogically not so good because this was the original thing. So these bonds here now, they are just going to represent it by there's this bond that I'm drawing. Maybe I use green, and I also redraw these guys here. So these bonds here, green. These bonds are the R matrices. They are really matrices. They live on the bonds, and they are connecting, as we know, is IR, I plus 1L. So people actually connect these. Looking right now. You see, this is a one-dimensional 2 state. Take a two-dimensional R. Yeah, and essentially that's it. So the state you get is this. We can write it as so, and what you're going to get is the very last M for open boundary conditions. The very last M. So okay, so maybe I should highlight this I plus SIL, or SL, and here's S1. Yes. The very last M's on this side have nothing to contract to. So these guys are the physical indices, and we are contracting them to our beta states. That was a bigger question. So this guy here, this tensor, this matrix product state, we project these S's. They're all contracted to our beta states here, and then we find a solution in which then we introduce this artificial index in here because of our exact solution. We can write down this state as a matrix product state using this two-dimensional variable sigma in an appropriately chosen R, and then sigma 1L and sigma 1 lowercase l, sigma L lowercase r, they remain uncontracted. And these guys here are therefore three indices for any four possible combinations of sigmas, so each of them can take two values. For any of these four combinations, the energy is unchanged. So these guys are my spin on half-edge states. So these guys here, spin on half-edge states. Of course, you can also put the thing onto a closed boundary conditions, then you close it up, and then there is indeed no boundary degeneracy. Yeah.
Suppose you want to create a Newtonian which is not exactly like the one you wrote. Yes. But a little bit different. Yes. You change a little coefficient in the last by quadratic term. Yeah. How stable is this type of velocity?
Well, let's say introduce this parameter kappa, and well, definitely we can take kappa all the way to 0. I forgot how exactly, also some negative values. People have studied these chains in great detail. numerically and found the phase diagram. I don't know, as far as parameter kappa, where exactly the limits are. But clearly it goes into negative and it goes above 1. That I know for sure. So this choice here of the biquadratic term equals 1 is deep, or 1/6. This is deep in this phase. Now, what I did not show you is what I mean by phase. I didn't show you that there is such an excitation gap. I mean, this is something we can maybe see that what we have to do to create excitation, we have to break such a bond, and that obviously costs energy taken. But I didn't show it explicitly. So, but there is a many-body gap that essentially protects you from going directly to symmetry.
Could you repeat why this number is the translation?
Yeah. Okay. So, well, the construction that we did is we solved actually a slightly different model in a slightly different Euler space. So maybe I repeat why this guy is a ground state. So a ground state is a state which is, a ground state has the property that, given that this is positive semi-definite, if you find a state which is annihilated by the Hamiltonian, it must be the ground state. We know it's positive semi-definite because these are bunch of projectors, just some of projectors. Why is this red, like this state here, annihilated by the projector? The argument was that within a blue box, we only have states in the sectors 0 and 1 for this two combined Hilbert space of 2x. While the projector is onto the S equals 2 part within the two within this blue sphere or rectangle, and therefore P on a BBS state is 0. And because the projector only projects onto the spinning part. Okay.
So let's go to this either 0, and that's the reason why.
So within here, S total, you mean S total square?
S total square now.
Yeah, it's 0.
Yeah.
Alright, so we have 2 minutes, but maybe it makes sense to use these 2 minutes at the end of another lecture or so. I don't think it makes sense to start something new now.